Hello, this is Ryunha, and today I will introduce the paper Generating Traffic Scenarios via In-Context Learning to Learn Better Motion Planner, which has been accepted at AAAI 2025. Before diving into the details of the paper, let me first provide some background knowledge on autonomous vehicles and related research. The vehicle that executes autonomous driving is referred to as the ego vehicle. The component responsible for generating the path for this ego vehicle is the motion planner, a key element in autonomous driving. It generates paths that ensure the vehicle's movement is smooth, safe, and efficient while avoiding obstacles and adhering to traffic rules based on real-time sensor data and environmental information. In other words, it acts as the brain of the ego vehicle, and training it effectively is one of the most crucial challenges in autonomous driving. Naturally, training a motion planner requires a vast amount of high-quality data covering diverse situations. However, collecting such data in real-world environment is extremely difficult. To address this, researchers have focused on collecting datasets in virtual environments. One key research area involves using LLMs to generate appropriate traffic scenarios, and the paper I am introducing today is one such study. This paper identifies the high cost of manually creating scenarios for dataset generation in autonomous driving as a major problem. Additionally, it points out that existing studies fail to include various hazardous situations. To overcome these issues, the authors proposed the AutoSynGen framework, which enables the generation of diverse scenarios at a low cost. AutoSynGen leverages LLMs to efficiently create a variety of scenarios and applies them into external simulators to generate high-quality datasets. Furthermore, it fully utilizes the capabilities of LLMs, eliminating the need for additional training or fine-tuning. Now let's explore how AutoSynGen works. First, the user inputs a natural language description of the desired scenario, providing details about traffic conditions, obstacle, pedestrian behavior, or unusual events. For example, a scenario description might include: there are 10 pedestrians on the road, and some vehicles' doors are open, or such. Such description allow for a diverse set of situations to be explored in training. The filter then performs an initial verification of the input to ensure compatibilities with the simulation environment. By referencing simulator documentation, it identifies and removes unsupported terms or converts them into similar, valid ones. This filtering step ensures that the generated scenarios align with the capabilities of the simulator while preserving essential contextual details. The LLM then processed this refined scenario description, incorporating in-context learning examples to generate a code-formatted response without requiring fine-tuning. By leveraging its understanding of structured comments and scenario logic, the LLM converts the natural language description into a well-defined configuration script that adheres to the simulator's format. This step enables the automated generation of complex and highly varied traffic situations. The validator further refines the generated code by conducting a second verification step against simulator documentation. It removes or modifies any unnecessary or unsupported code sections that may cause errors during simulator execution. Once the validated config file is finalized, it is fed into the simulator, which then generates the corresponding environment according to the specified conditions. By running this generated environment, the dataset can be automatically collected through repeated simulations, capturing the information of environment and sensors. Now let's focus to the evaluation steps. To compare with the target dataset, the authors trained a motion planner using 3 datasets. The target dataset, the dataset generated using AutoSynGen, a combination of the target dataset and AutoSyn dataset. All 3 datasets were used in the same training method, and their performance were evaluated and compared. The following table presents the results. 2 motion planner, training methods, traffic predict, and traffic were used for training. The models were evaluated using average displacement error and final displacement error. These metrics measures how much the generated trajectory deviates from the true trajectory, thus lower values indicate better performance. The target dataset to compare is the Apolloscapes dataset, which is the large dataset from various locations in China under varying weather conditions, which indicates SAS in the table. As shown in the result, the dataset generated using AutoSynGen consistently outperformed others. The next graph visualized the result using traffic predict method, displaying epoch progression and corresponding performance scores. As mentioned earlier, lower scores indicate better performance, so smaller circles represent superior results. The dataset collected from AutoSynGen demonstrated the high accuracy in trajectory in the various epochs. Moreover, combining the AutoSynGen dataset with Apolloscapes improved overall performance. As the number of epochs increased, the dataset combinations show progressively better performance. Unlike the case where AutoSynGen dataset alone result in unusually high scores for certain metrics, the combined dataset demonstrates a more balanced performance overall. This result indicates that the dataset generated by AutoSynGen maintains a quality comparable to real-world datasets, and then that combining the two effectively increase the dataset size for improved training. Thank you for watching.